Hello, Spark Summit. My name is Nate. I'm a data architecture consultant, and I focus on the area of industrialized machine learning. So this is just the term that my employer uses to refer to the work we do in machine learning, which is focused not just on the data science, but also on taking the research outputs of that data science and putting those into production. So having the opportunity to work at this intersection of data architecture and machine learning, I've had a lot of exposure to this emerging concept of the feature store. So that's what I'd like to talk about today. I'd like to provide an overview of this space, of the feature stores that are becoming more popular. I'd like to describe an approach to implementing feature stores, which I use in my day-to-day, and I feel like it might be a little underrepresented. And then at the end, will provide a demo of how you might be able to take some of these concepts and put them into production for yourself. Before we dive into what makes some of these approaches to feature stores different, I want to start with what makes them the same. What unifies all of these approaches is that there's a common problem that we're trying to solve. It's a challenge I've had to address on every data science team I've had to work on. There's this fundamental tension between the scientific nature of the work that we're doing, the experimental nature of the work, and rationalizing that with the fact that for every one of these iterations, we have to be creating business value. So what we need is the ability to tell a more complete story about the business value that we're creating with data science at every one of these iterations. And one way that we can do that is at the outset of every iteration, of every experiment, we can be really clear about here's the business hypothesis that I'm setting out to validate or invalidate in this experiment. And if we validate our hypothesis, we create lift in production, we advance some KPI, and we've created value that way. But regardless, even if we invalidate our business hypothesis, we've still created some business insight from that. We've learned something. And what's critical is that I'm not learning this as an individual, but I'm capturing that insight in a repository to accelerate future research. And one of those repositories that we can use to capture those insights is the feature store. So in other words, the feature store, when we're using a feature store, every experiment that we're doing is accelerating future research. Now, one of the original intentions of this talk was to do a survey of a lot of the material that had already been put out here on this topic. And in doing that research, I identified this resource. This is a relatively new resource that's come out that's done a lot of that legwork for us. So a big thank you to featurestore.org. It means today we can focus not on surveying so much everything that's been put out there, but we can talk about how these approaches are distinct, and we can dive deep into one of these approaches. So do your own research. You're not going to find every commercial product available on this site. But it's an excellent resource. So thank you to the guys at featurestore.org. And there's a lot of ways to break down these different approaches. The one that I've chosen is to identify what's being automated in each of these approaches. As an engineer, what's the effort that I no longer have to do when I'm deploying a machine learning application? And by far the most common approach here, the most common feature store implementation is where we're automating the delivery of the data to the scientist or to the production application. And the most common question that occurs with this approach is, how is this different than my existing data management and data governance framework, right? I already have a data catalog. I already have strategies for managing my ETL runtimes. What's new here? And the way that I answer that is that when we're working with these machine learning applications, we want to extend that framework. We want to extend that governance framework to capture some of the nuances and edge cases of our machine learning applications. So here's an example of that. An example of some of the semantics we might need to extend our data governance framework with. If you're not doing machine learning, you're probably not dealing with training and test data, but here's why you might want your governance framework to be aware of these concepts in the context of machine learning. Here's a typical example of what we might be doing when we're deploying machine learning applications. Say I have some sales data. One of the first things I might want to do with that sales data, I might want to create some customer segments. Depending on the model I'm creating, what I'm probably going to do is I'm going to break my data down into a training set and a test set. I do some machine learning. I create that produces a model. The model makes predictions. And then crucially here, the output, those predictions are themselves features that can be used to accelerate future research. So this seems like the ideal scenario for a feature store. I'm creating a business insight. I'm using that to accelerate future research. In this case, that future research might involve building a model of next best action. Clearly something that could benefit from customer segmentation. So similar, I'm going to join that customer segmentation to some other feature data from my source data. I'm going to do a train test split. This seems like the ideal scenario for a feature store, but what has gone wrong here? So if we were to build this model, what we would probably find is that the model performs really well on our test data. And so we would continue to tune our model, and we would continue to perform really well in our test data. And then when we go to deploy on our model, we would find that our test data is, our performance on our test data is not a good signal of how our model is going to generalize to unseen data, right? The fundamental reason we want to create these training and test sets is to give us that signal so that we know if we're overfitting our model. What we might find in this system here is that our test data is no longer providing that signal. And the reason for that is that information about our test data has snuck into our training process through this segmentation feature. So this is an example of why you might want to extend your data governance framework to be aware of these training and test semantics or other machine learning semantics. In theory, we want to deliver our data to our scientists or to our production applications in a way that helps us avoid this situation. A second approach to management of features. There are a number of approaches out there which describe how we automate, not the way we deliver the data, but how we do the ETL that's involved in the feature engineering. So a number of scientists have observed that a lot of the ETL that we're doing during feature engineering feels repetitive. It feels like something that can be automated. Window my data based on these dimensions, pivot my data based on those dimensions, create a whole bunch of features, feed that into a feature selection algorithm. And that could be a more automated method to feature engineering. So this is another class of approaches to feature management that's out there. And where I'd like to spend the remainder of this talk diving more deeply is on the automation of how we construct our machine learning pipelines. So one example of automation in constructing our ML pipelines is the methodologies behind AutoML, right? And these are methodologies that target the citizen data scientist, the data scientist who may not have a depth of knowledge in algorithmic design, but can still benefit from machine learning. And what I'd like to share today is an approach to automating the construction of our ML pipelines in a way that targets the folks who are doing that algorithmic design in a way that lets us expose an API to them, which is not doing the algorithmic design for them, but instead isolating the concerns of the operations of wiring the pipeline together and deploying that pipeline so that they can focus on the algorithmic design. So for the uninitiated, what are we talking about? What do I mean when I say ML pipeline? Some of us may have a vision of how machine learning works. There's a common vision of machine learning which focuses on the very last step of machine learning, where we have an estimator which is taking some featurized data, our final featurized data set, and then doing something like a logistic regression or a decision tree to make a prediction. When in fact, in an industrialized context, this is typically the last stage of a whole pipeline of estimators, each estimator creating features to feed downstream to the pipeline. An example of that is the example what was provided earlier. I might, as a first step of creating a next best action model, I might do some customer segmentation, right? So these multiple estimators get assembled into a pipeline, and that full pipeline is what gets fit for our data. And what we found when putting these types of applications into production is that it's crucial that we manage not just the model that comes out of that pipeline when we fit it to our data, but the artifacts in the pipeline itself. We need the same level of insights and controls into the pipeline as we need into our models. And so here's what that looks like in code. This is from the Spark documentation. It's just a quick start documentation for, this is what a pipeline looks like. We are defining some of the stages of the pipeline. In this case, we have a hash. We're vectorizing our inputs using a hashing estimator. And then that gets fed into a logistic regression. All of this gets wired into a pipeline. The pipeline is what gets fit to our training data. And then that outputs a model. That model makes predictions, which we evaluate for model quality. And the basic insight behind the approach I'm going to describe in the last few minutes here is it comes down to this question: why does this line of code exist? Is it here just for syntactic purposes? Or what I'd like to convince you of today is that, in fact, we have all of the information at this point to construct a pipeline implicitly without having to explicitly wire together these stages. And by doing so, it creates opportunities for us to optimize the construction of that pipeline and layer governance on top of it. So let's talk about that algorithm. And first, as a point of contrast, let's talk about how these pipelines normally get deployed, or typically get deployed. So here's a pipeline very much like the one we saw in code. We're doing some tokenization of text, we're vectorizing that text, and then we're building an NLP model on top of it. In our first scenario, we're creating a sentiment model. Now, often what will happen is I'll deploy this sentiment model, I'll go into my next experimental iteration, and now I want to deploy a new kind of model. Maybe I want to try and make some inference about the toxicity of text rather than the sentiment of text. And all too often what will happen is this sentiment pipeline will exist in a notebook. I'll copy paste large portions of that notebook, and with it, I'll copy paste large portions of the pipeline. There will be a lot of redundancies, not just in the code, but also in the computation. These featurization steps can be very computationally expensive. And now if I try to layer any governance on top of this pipeline or automation on top of these pipelines, that's also getting copy pasted all over the place. So as an alternative, what I would like is to be able to declare the stages of my pipeline. And given the correct metadata about my pipeline, in particular, what do I need to come out of my pipeline? In this case, I need a sentiment prediction and a toxicity prediction. I can write a relatively naive algorithm which works backwards to construct a pipeline which is maybe a little bit more optimal. So I've not just removed a line of code here, but I've also, by implicitly constructing the pipeline from stages that I've declared and some metadata that I've declared, I've already seen some early optimizations that I can do when I construct this pipeline. But so far, this is a pretty simple algorithm. We can take a look at a more interesting case. In this case, we want to experiment with two different strategies for vectorizing our text. right? So maybe my sentiment model will perform better if I use a different strategy for turning my text into a vector. And if I construct this graph in the same way, what I'd find is I can't actually feed this graph into Spark. And the reason is I have multiple incoming edges to a node, right? And Spark needs to know exactly where to get its data from. There can't be this level of ambiguity. It needs to know, my sentiment estimator needs to know where to get its vectors from. And so one solution to this problem would be to reconstruct this graph by reconstruct it from the possible traversals of our original graph, right? And that would look a little something like this. And there are some interesting applications here. I have some applications for A/B testing. I can compare how my pipeline performs when I use WordVec as my vectorizer rather than when I use TF-IDF as a vectorizer. So that's already sort of emerging just from this algorithmic approach to implicitly constructing the pipeline. But another thing that's emerging here is some really interesting metadata. So from this, I naturally have metadata about data lineage. I know where my sentiment model is getting its predictions from, and I know how that data is constructed in turn. So these are opportunities for better management of our operational tasks, such as metadata management and runtime optimization. And they come just from the algorithm itself. But the real value here is our opportunity to create new types of APIs based on this algorithm. And the real way that I get accelerated from an operational perspective here is because it's the fact that I can now build APIs that better isolate the concerns of the algorithmic design from the operational concerns. How am I building my pipeline? How am I constructing it? My DevOps, how am I deploying that pipeline? The automation around the runtime management, the metadata management and discovery, as well as how I layer governance on top of that pipeline. So with that, I'm going to provide a demo of what an API like that could look like, as well as an example deployment from that API that indicates some of the new ways that we can interact with this metadata and layer governance on top of our pipelines. So after the demo, I'm handing things off to Nate of the future to answer any questions you have. I hope you'll stick around for those questions and also to provide feedback at the very end of the talk.
The FeatureFlow ML pipeline orchestration algorithm creates new opportunities to write APIs that separate the concern of algorithmic design from our operational concerns, concerns such as metadata management, runtime management, and governance. So here's an example of such an API implemented as a library to be used as part of a ADO deployment pipeline. So here we are doing just some typical algorithmic design, defining some stages of our ML pipeline. In this case, we are defining some NLP tokenization strategies and building a sentiment model out of that. And recall that we don't explicitly wire together the stages of this pipeline. We rely on the FeatureFlow algorithm to do that, but we do define some metadata around our pipeline. And specifically, we're telling the algorithm, here are the outputs that I'm expecting. Via one means or another, I'm expecting a sentiment prediction, and I'd like that to be joined to the text that was provided as input to the pipeline. So noticeably absent from this these algorithmic concerns are integrations with our operational tools, such as our MLflow model management tool or our Databricks runtime management tools. Those concerns are instead handled hidden behind this API. Right. So in particular, for all of the pipeline stages we have defined, we now have this API method which can be used to deploy those stages. So here, all of those operational concerns, governance for how our pipeline is evaluated, all the sticky details of how to configure our cluster, all of that has been captured in a reusable way as part of this API. So to make that more concrete, here is an example of what a deployment like that might result in. Here we've the API is managing 3 jobs for us. We are managing a job to fit our pipeline to the data that that's been provided. And then because the output of that pipeline is a model, which we store in the model catalog, and the model catalog has this notion of staging model and production model, we have 2 jobs for making predictions using models from the model catalog, one for making predictions using the model that's been promoted to staging, and the other for using the model that's been promoted to production. So all of the details for integration with the MLflow model management have been encapsulated into these jobs, and we can expect, we have controls around and guarantees around what metrics are being collected, what standards are being used to collect all of this data in MLflow, as well as the model catalog. So now what about metadata management? When we did this deployment, we captured all sorts of metadata about our pipelines. Where did that metadata end up? Here you can put it anywhere. Here we demonstrate a UI we threw together, and this helps to illustrate some of the additional insights that can be created by managing our pipeline stages, our featurization stages, in addition to managing the featured data itself. So, for example, in addition to searching for features such as text vectors, I can also identify the relevant stages which are consuming text vectors, or what strategies I have for creating text vectors. Scientists can compose these strategies and share them with one another. Also, because I'm managing not just the featured data, but also the pipeline, I can tie these pipelines to the featurization stages. So here we can see this is some information about a pipeline where this featurization stage is being used. I have a simple visualization of how this pipeline's been wired together. And so I have insights into the pipeline, but also because I'm managing the runtime, I have insights into that runtime. So here we're capturing, using a popular visualization called the facets visualization, we're capturing some of those runtime metrics.